Today's speaker is Dr. David Weinstein. David is a postdoc in Eilat, the Interuniversity Marine Science Center, working with Adi Torfstein. He got his PhD at the University of Miami in 2014, working with James Klaus, and then did a postdoc in the university that I cannot pronounce.
Ryukyus. University of the Ryukyus.
Okay, in Japan. And then came here to Eilat. He's interested in coral reef, sedimentology, and ecology. And today he'll be talking about can modern reef accrete, sedimentological development of mesophotic reefs in the US Virgin Islands. Next week, we do not have a seminar because of the AGU fall meeting. The week after, we'll hear from Shadef Smatov. Thank you.
Can you turn the slide off a little? Is that possible? All right, thank you so much for that introduction, and everyone, thanks for coming this morning. Again, my name is David Weinstein, and so I'm going to be discussing my past research at the University of Miami, considering the sedimentology of mesophotic reefs in the US Virgin Islands. And so this talk is really going to be all about structure and building up structure. And I think being here, you all have experienced the process of developing structure. Maybe not always so happily, but you've witnessed it. And structure is important because structure is the foundation for diverse, healthy ecosystems. So just like here in Jerusalem, we need all the buildings to support the biological entities, you all who live here, to help with commerce, to tourism, to support the life. It's the same thing with coral reefs. So I really love these pictures, because to me it almost looks like a coral hotel. You really see how the structure provided by the coral creates a habitat for obviously fish, but all sorts of vertebrates that are also living in. So the structure of the reef is vital for creating a healthy ecosystem. Now, one way to consider how structure changes in a relatively short amount of time is a carbonate budget. I'll talk about the specifics of the carbonate budget soon, but just briefly, it's just a mass balance between the amount of carbonate that's added to a reef system versus the amount that's removed. So carbonate budget analysis has gained some steam. It's been done in the past, but it's been more very quantitatively been conducted all throughout the Caribbean by Perry et al. And what they found was unfortunate. They found that 53% of the transects that they studied were in a status equilibrium. So they were barely creating material, or they were actually losing material. So we've heard in the news, and I've seen, I don't know if you've been there, the Caribbean, the health of the coral reefs is doing very poorly. But this shows that the structure is also doing poorly, that we're losing structure. There's even been studies showing that the reefs are flattening with time. You're losing structural relief. And the problem with that is if you lose the structure, you lose what the structure provides. So like we talked about biodiversity, people aren't going to want to come and support the economy, the tourism. If the fish aren't there, it's not pretty. You're also going to lose the fisheries because the fish aren't as abundant if we have low structural relief. You lose other aspects like pharmaceuticals, and coastal protection, yada, yada, yada. So that's in terms of short-term change. But as geologists, we usually think about on a longer-term time frame. So when we talk about structure in terms of coral reefs, we're often talking about reef accretion. And so reef accretion is considered the vertical accumulation of carbonate with time, and it's usually measured directly measured with cores. So if you're not familiar, people will take cores in carbonate deposits, reef carbonate deposits, and they'll date two different horizons where they can, and they measure the vertical displacement between those two dates, and they give an accretion. Now, the prevailing assumption in reef accretion is that reef accretion decreases with depth. And the main reason for this assumption is that most coral species growth rates tend to decrease with depth. Now, that's a very big generalization, but it's been shown for various species that coral growth decreases with depth. And so there's an order of magnitude difference with accretion based on you have to fill in all the different spaces in the three-dimensional reefscape But the idea's theory is that reef accretion decreases with depth. And the problem with that is, well, not a problem, but the implication is that depending on the depth you are, if you're too deep and you're not able to produce enough material to match the change in sea level, reefs will drown. So understanding reef accretion is very important for the development of a tropical carbonate shelf that's based on reef limestone as well. And so, as we said, the idea is that accretion decreases with depth. However, that's kind of an assumption. It hasn't really been tested very often. So in 2009, Hubbard went and took about 150 different cores all throughout the Caribbean. And what he found was that this prevailing assumption that reef accretion decreases with depth didn't hold up under analysis of the cores that he looked at. And so it really makes us wonder, is this assumption that reef accretion decreases with depth, is that a general rule? Is it real, or is it just a misguided theory? And so what I also noticed about this is that there's still very little data for the deeper reefs. Especially, there's no direct measurements of modern mesophotic reef accretion. And so that's what I'm interested in, is how these deeper reefs may be accreting in the past, in the recent past, and currently how their structure is changing in time. Now, if you're not familiar with mesophotic reefs, I just want to explain, this is your classic reef zonation that you would find in the introduction textbook. It's not like this everywhere, but this is, your idealized example. Mesophotic reefs are defined as deep reef communities approximately between 30 and 150 meters in low light, low energy environments. I say approximately 30 because really the definition is actually more based on the ecology. And so you're talking about changes in the morphology of the coral and the amount of symbionts and the way that they're layering in the coral and the associations of different ecological communities. But that's the generally accepted term. And so the idea is that it's kind of a transitional stage between shallow light areas and deep dark areas. And so people have used the term the twilight zone to refer to mesophotic reefs. And they're important for a lot of the same reasons that shallow reefs are important. They have high biodiversity. They're really important for fisheries. Where I worked in the Virgin Islands, it was a protected area for grouper. It was a grouper spawning site. So if you like to eat grouper, it's a reason to be concerned about these areas. There's also the issue of the refugia hypothesis, that shallow reefs are currently threatened, but the deeper reefs might be less impacted by anthropogenic influences. And so if they're less impacted, that these coral reef organisms might be sort of protected in a deeper environment, and there might be possible connectivity. And so people have looked into that as a way to kind of, with the worry about what's happening in shallow reefs. Can the deep reefs help save the shallow reefs? But there's also a lot we just don't know about mesophotic reefs, and it's a really interesting area to work in. Now, there's been a lot of great work done recently with technological advances in mesophotic reef research in the U.S. Virgin Islands, where I did my work. There's been great work previously done in Eilat. Some of you might be familiar. Really groundbreaking studies have been conducted there. I did some work in Okinawa, Japan. Ryukyu, that's why it's called University Ryukyu. Looking at coral recovery after storms. But the problem is that most of the work has been biological and ecological in origin. There really has been very little examination of modern mesophotic reef structure. And so that's what really interests me to this project. And it's also to note that mesophotic reefs, at least in some areas, might have a greater spatial extent than shallow reefs. So we haven't always been able to get to deep reefs, but they might actually represent a bigger part of the tropical marine ecology than their shallow counterparts. So it's really important to kind of consider these deep reefs into our models of carbonate development and ecological development of tropical marine ecosystems. So I'm interested in the structure and change of mesophotic reefs, and I started thinking, well, based on uniformitism, we would expect that there have been mesophotic reefs in the past. And I was wondering, well, have they built up significant material? The idea is that people think that reef accretion decreases with depth. So going into recent literature, I find examples where there have been significant development of reef material in what has been considered mesophotic conditions. I say mesophotic conditions because it's very hard to determine exact depths of these deposits, especially it's easier for shallow areas than for deep areas. So it's not certainty, and this is based on morphological traits of some of the corals and also associations with bed forms. But the authors believe, and I'm pretty convinced also, that these are deeper environments. And the interesting thing is you're really able to produce a significant amount of material. It also, by the way, might be these were in deltaic systems, mixed carbonate clastic systems as well. It could be that they were just darker environments, but based on the analysis of these studies, it's likely that they were in deeper water. And this is also important because there's theories that coral reefs, actually sciloctinian coral reefs, started off in these deeper environments. So understanding the buildup and development of mesophotic reefs is actually important for understanding the evolution of coral reefs in general, as we know them. So we showed that we have had development in the Cenozoic of coral reefs. Now going back to this graph, we noticed that there's a decline of the net geomorphic production. That's basically a loss of material versus gain in the Caribbean. But what's really interesting to me about this graph is there's no information on deeper areas. So I'm trying to form that connection between modern study of changes to reefs currently and what the implications might be towards the future and how mesophotic reefs may have accreted in the past. And so that's kind of the driver between my research and understanding the structure all changes. And as we say, the structure is important currently because that creates the habitats. So just a generalization of what I'm doing is the first main question is, are U.S. mesophotic reefs accreting? And that's kind of a weird question asked because we're not looking at long-term accretion. So basically, I'm asking, what is the geomorphic production? Where do they plot on that line? Are they positive or negative? And using that infers that they may be accreting material. And about that is, are they able to maintain structure? If they're accreting and building up enough material, they can theoretically create structure to support habitats. I was also, a sub-project was wondering what the variability of carbonate production is in mesophotic reefs, especially in the Virgin Islands. We have a lot of different habitat types, architectural types, and I'll explain that later, but I was also curious to see, do we have differences in carbonate production? Because obviously it's more complicated than just if it's decreasing like that. The second question is how does potential modern U.S. Virgin Islands mesophotic coral ecosystem reef accretion compare to shallow reef accretion and accretion in the past? And what are the implications for the traditional reef accretion theory that we talked about, the decrease with depth? So first I'm going to go over the carbonate budget analysis that I use. There's different methods. Some people use chemical methods, looking at the seawater alkalinity. I think some people have done that here, but that's not the method I do. So I'm going to explain the method I use for this study. It's a census-based method. Then I'm going to talk about the sites that I worked in to look at mesophotic reef carbonate production. I'm going to talk about the methods. Now there's a lot of different components to the carbonate budget, so I'm going to go through each method and I'm going to talk about the intermediary results so you know as I go through a method what direct results come from that method. But then I'm going to put that all together into the results of the carbonate budget, and that's essentially where we plot on that vertical graph of positive versus negative. And then we're going to talk about how we can think about that in terms of accretion and how mesophotic reefs might be producing structure and continuing to do so. All right, and on the, if you get lost, I know I'm talking, there's lots of information, so I kind of give a little outline here. So if you're not sure where I am in the talk or fall asleep, you can just look there to see. All right, so the carbonate budget, we use it to evaluate reef structure and controlling factors and assess the structural sustainability and reef accretion potential. Essentially, it's the balance between constructive and destructive carbonate processes. And there's three main processes we consider. Two of them are constructive. First, we have primary coral production, And that's essentially the main framework builders of a coral reef is coral. So that's the primary production of the corals. Then we have secondary production. That's all the other calcifying organisms that might produce carbonate material. And we're not talking too much about sediment additions. In this region, we don't have a lot of sedimentation. So these are the three main components for this budget. So we have, for the constructed, the secondary production as well. So crustose coralline algae, forams, mollusks, and other organisms. So that's the constructive. Those two together are what we call the gross carbonate production. Then on the destructive side, we have bioerosion, and that's the physical or chemical removal of erosion by organisms. And so this is usually done by grazing organisms such as echinoderms, sea urchins, and parrotfish, and then you have macroborers like boring sponges and mollusks and spunculates, and then you also have microboring organisms. And so that's the negative or the destructive aspect of the carbonate budget. And so what we do, we have these three processes, we try and find the rate of these three different processes. But we can't stop there. We have to apply those rates to what's actually on the reef. And so to quantify what's on the reef, we use standard methods of reef rugosity and cover. And so rugosity, we use a basic chain method. We drape a chain over the reef, and we put it into all the cracks, and we see how long that is versus if we pull the chain straight. And that gives us an idea of the three-dimensionality of the reef. And we also have cover, which is linear coral, how much coral or dead areas of the reef are there based on a two-dimensional frame. And so we multiply these two factors together to get what we call a spatial cover index. And so that basically tells us the benthic cover and three-dimensionality and approximation on the reef. And then, like I said, we scale that by the three main processes. Now, those three main processes, we also have to consider what's the living parts of the reef and the dead parts. It's an oversimplification, but to approximate, we have to consider how these different processes relate to different parts of the reef. For primary production, it's just the corals itself, so we don't have to worry. But for secondary, we have accretion. These organisms add on to dead parts of the reef, but they will also grow on to lower underside, the platy bottoms of mesophotic corals and other corals. We have to consider that. And with bioerosion as well, you have organisms that that will bioerode the dead parts of the reef, but also some organisms, very few, penetrate living substrate, but also you can get underneath the substrate. You have to count for that in terms of carbonate loss as well. So, but it's a very complicated, but overall it's just a mass balance. Like I said, you add the two processes that add carbonate, you subtract the process that removes carbonate, and you get what we call net carbonate production. I do have to note, we do other correcting factors. Not all material that's eroded is actually removed from the reef. So we have to factor which organisms are actually doing the erosion, and we have to account for sediment retention based on hydrodynamics. And so we do some corrective factors. So that's the carbonate budget. Essentially, we're seeing how much material is added versus removed in the U.S. Virgin Islands. So this is my site location. There's a little map on the side to show where we are if you're not familiar. And so this is the northern U.S. Virgin Islands where I did my work. So this is a map of the shelf here, or part of the shelf. And we had 4 mesophotic reef sites indicated by the various circles and 2 shallow sites for comparison. You'll note, and I'll show a little earlier, that there's actually a very interesting structure in of itself. And that was what I was talking about, that there's different types of habitats within the mesophotic community. And so I also wanted to look at variability in those sites. So just quickly, I'm going to explain the sites. So first at this primary bank. It's a long linear expanse, greater than 1 kilometer, and this is important, greater than 5 meters of relief. And this is just at the shelf drop-off. Next, we have the secondary bank. So we have a double reef system. It looks like a double barrier reef system that's been drowned, but we have this secondary bank, and it's just like the primary bank with greater than 5 meters of relief, but it's a little broader in extent. Next, we have what we call the hillock basins. It's a little hard to see, but if you can see, there's kind of a shade here of these mounds that are created. It's an unbroken expanse, a flat area with 3 to 10 meter tall, what we call hillock structures. And in between, you have rubble piles and some standing coral. Finally, we have what we call the deep patch. And so it's a relatively low relief, but we still, you do notice that there's plenty of, a lot of coralline algae, rhodoliths, and some coral production. But there is structure here where next to it, in these areas, there's absolutely no structure. It's just sand. So we're considering that in geologic terms of reef buildup. So I'm talking a lot, and there's a lot of information. I use this kind of just to help myself visualize these different sites. And so you have this primary bank. It's kind of narrow and long. The secondary bank is a little wider. These are these hillock structures and these lower relief deep patches. Now we also have 2 shallow sites for comparison to understand differences. And so these are just pictures of those sites there. Now, throughout the talk, I'm going to talk about, I'm going to give results. And I know some of you might already be lost, and I apologize. There's, like I said, a lot of information. But I'm going to do my best to let you know which sites I'm talking about. So usually I'll have this theoretical cross-section or that map so you can kind of correlate between which sites are which. And hopefully that'll help you kind of understand the results. In the effort to save time, I'm not going to give the results of the spatial cover index, but just say that we did find significant differences in coral cover and rugosity between the sites. But in the linear banks, the outer sites there had much more higher coral cover than the inner areas there. Is a main takeaway message. All right, so now we know the site, and we want to talk about the actual methods of developing the carbonate budget. So first, we want to look at the live parts of the substrate. So these arrows are pointing to the reefs that are currently living. And so going back to our 3 main processes, we're talking about the primary, the coral framework production, okay? And so we want to get that primary production. So to do that, we get the calcification rate times that spatial index that I talked about. And we do this for the primary coral that's in the mesophotic region over Salafranci. So we collected a whole bunch of this coral at 3 of the 4 sites. It didn't occur at that low relief deep patch site. But the other sites, we collected it, we sliced it up, and we got the cross section, we x-rayed them, and we did that to try and find linear extension rates. It was a bit difficult, but we confirmed with stable isotopic analysis that these, what we saw was indeed linear changes that were on an annual scale. And again, we published results of this in 2016. I can't go over the specifics now, but we did confirm that it is annual growth. And so we find this linear extension and we multiply it by bulk density, which we do basic buoyancy weight methods to figure out what the bulk density is, and that gives us our calcification rate. On a side note, we published earlier results of the coral growth rates we got at that 3 sites. We found, you can't really see in this graph, but we did find some variability between sites. And we also found it's important to consider bioerosion in those areas. But we also, more importantly, found that the growth rates fit within expected trends. So we were pretty confident in our results. And also, we were pretty happy that there really hasn't been that much work done in the deeper water. A few studies, but we really expanded the breadth of knowledge for at least this coral type. And at least for this coral type, confirmed that coral growth decreases with depth. So we have that, and like I said, we multiply, these are the linear extension. We multiply that by the bulk density that get the calcification. Unfortunately, we couldn't collect coral for all species that were present. Even in the Caribbean, we have a lot less species, but still we just couldn't collect them. Fortunately, at the 3 main sites where we collected Orbicella franci, it was usually 70 to 90% of all the coral was that species. To supplement that, in the deep sites, And also in the shallow sites, we used the reef budget methodology, and they have coral growth rates and densities of all the corals, of most coral species in the Caribbean. And so we took those measurements for the closest depth and closest location and supplemented our data with that to get primary production rates. And so I'm going to show these graphs now of what the carbonate fluctuation is. But please note that these are taking those rates and then scaling them by what's actually on the reef. So even if you have a high carbonate production, if there's not much coral cover there, the value is still going to be low. So it's important because even if you have a lot of growth, if the coral's not there to grow, it's not adding material anyways. So there's a way to kind of take ecological surveys and match them with what's actually on the reef. And what we found was there was significantly different primary production at all mesophotic reef sites. Interestingly, the two deepest sites had some of the lowest production, but they were still higher. The mesophotic sites were higher than the shallowest site. Part of that was because the coral cover in the shallow areas is pretty low. There's been a lot of decline in shallow water recovery. Interesting, they picked this site, colleagues of mine, because it has been doing well in coral cover, and because of that, and because you have coral growth rates that are quicker in those depths, you have a higher production there. All right, so that's that coral framework part. That's the primary production. Now we're looking at the other processes. So we want to find out what's happening on the living surfaces of the coral in terms of accretion and bioerosion. And to spare details, not a lot. You have some removal on the undersides of these platy corals in the mesophotic reefs. You have some accretion, and you can show a little accretion here, but it's not significant, so I'm not going to go over those results too much. But I just want to say that we did account for that. So that's the living part of the reef. Next, we're going to the dead part. We have to consider how much material is being removed or added to all these parts that don't have coral covering. They might have sparse algae, but we essentially assume they're available for bioerosion. Unfortunately, we don't know how old they are, so like we can figure out with the coral, so we have to use experimental substrates. And unfortunately, it's very hard to get that material in deep water based on the limitations of diving. So we used a course from shallower studies. We removed any type of external bioerosion, and we created experimental substrates, these discs. And then we put the discs out on quadrats. We had 3 quadrats per site. They were about 10 meters apart, so we can look for inter-site variability. And then we collected at 3 different intervals. And so this is showing different times as we collect and as we have erosion. We left one site for a 10-year study, but we're finding that they eroded too quickly, so they're not going to be around for the 10-year study, unfortunately. But here's an example of how much material loss you can have after 3 years. And just when we look at the amount, just looking at the weight change, and so not accounting for bioerosion accretion, we find a dichotomous initial bioerosion or weight change of similar substrates. So the deeper sites seem to add material to these experimental substrates, whereas some of the shallower sites are actually losing a lot more material. So that's really important. Interestingly, I don't fully understand, one of the mesophotic sites started to be not highly erosive, but then at the 3rd year it became lots of material loss. So as I said, we have correction factors for how much material is removed based on what organisms are doing the removal. So we had to try and understand what organisms are responsible. So to do that, we didn't have a CAT scan, so we cut it up like a pizza and imaged the cross sections. We found out how much of the material was originally there and how much was remaining to kind of give us an approximation of how much was removed by various organisms. We could account for how much accretion there was, but then we could also account for how much material was removed by different processes. You don't have to consider this is all types of basically grazing on the top, on the bottom, and on the outer parts. But basically, it's just grazing. And then we have macroboring, that's organisms you can see with your eye, traces that you can see with your eye. And we accounted for those processes. And then we also wanted to account for microborings. Now, we didn't actually do measurements directly because it's pretty extensive. So we did approximations based on studies at similar depths to give us an idea of microboring rates. And again, so we're taking we used the results after 3 years because we thought that was as much of an equilibrium in bioerosion as we could get based on the study results. And the accretion is based on rates after 3 years. And then again, scaled by the amount of dead substrate available for erosion. What we find was that there was a high relative substrate accretion. What I mean is relative is that all the secondary accretion rates are relatively similar at all the sites, but there doesn't seem to be a relationship between primary production and secondary production. So here, even though there's low primary production of the coral, it seems that secondary production is very important, even more important than the corals themselves. I have living framework accretion, but I showed you that that was insignificant, but it is on the graph here. Next, we look at the bioerosion processes, and we see a relative gross production similar to total bioerosion. So, at least for the mesophotic sites, the more material you have, the more material it seems that is also lost. Interestingly, we didn't find this in shallower sites. I'm not quite sure why yet. And we also found that grazing was the main substrate eroders, was the main type of substrate erosion. There was relatively little macro and micro borings. Now, this might also have to do with the substrates we used and the time that we had, because they were coral from shallow water. And so that has certain assumptions, but at least we can use it to compare between the sites accurately. It might make it difficult to compare with other studies, but we believe that these results are pretty accurate. That being said, we also believe over long periods of time, grazing seems to decrease with depth based on other studies we've done. Coincidentally, we did find that the loss of the rate of substrate weight change of those rocks was correlated to the biomass of parrotfish. So the less parrotfish you had, the less erosion you had. All right, so I know it's a lot of details. Some you may not have followed. Some people care about the bioerosion, other people care, So you might not get it all, but we're going to bring it all together now and see what the bigger picture is. What does all this mean in terms of the carbonate budget? And so to do that, we're going to go back to that image I showed you before. And so this is, are we adding material or are we losing material? And so what I can say first is I'm proud to say we extended the depth range of carbonate budget analysis. So there have been no studies to look at net carbonate production at deeper depths, and we've been able to do that. What we found was, interestingly enough, we have net carbonate production, positive carbonate production at all the mesophotic reef sites. The deep patch site, the one with low relief, is at that stasis. It's barely maintaining positive structure, but all of them are in a net positive state, which is significant because we said before, 53% of the other studies were actually in a stasis, barely changing, or they were actually eroding material. All right, we're running out of time, so I don't want to. There's another way to look at it, tertiary diagram mapping the 3 different parts of the carbonate budget. Essentially, where you plot on this line tells you that net carbonate production, where you were on the past graph, and depending on how high you are, tells if it's from secondary or primary production. So it's basically showing how much material is added based on those 2 processes. And the closer you are there implies that you're having more erosion, or you're having more erosion compared to addition of material. And so this is kind of how the results plot, but again, we see that they're all above that net stasis, so they're all in the positive net accretion. We also found, and this is what I discussed, that there's different pathways to maintain positive net production of mesophotic reefs. They don't all have to rely on corals. These two sites are having a high level of secondary production. So we have different pathways towards maintaining positive accretion in these mesophotic reefs. We also wanted to compare with if there's a temporal change. Unfortunately, the bioerosion and the primary production are long-term averages. So those we can use for different transects. That's been done in other studies. So we used benthic surveys from 3 sites in 2003, and we scaled the data by those benthic surveys. We had to use the same rugosity because they did not measure rugosity, but we would have actually expected rugosity to be higher as if the coral cover was higher. But what we found, and again, this is a loose approximation, but we found that that we could measure that there was a decrease in net carbonate production, in gross carbonate production between those 2 time frames, and we attribute that to a 2005 severe warming event that corresponded to more partial mortality. All right, so now we take all this and we think in terms of reef accretion. So we scale the net carbonate production and we use porosity estimates of 50% and density of aragonite to determine how much accretion you would have. And what we find is we have positive accretion because we have net accumulation of material, and we would think that these would actually be higher if we actually used those experimental substrates were made out of the coral that's in the mesophotic reefs, because you tend to have less bioerosion with denser material. So we would expect these to even be higher. And so we find positive accretion, and what's interesting is this positive accretion that we have is greater than in modern shallower reefs, in between 10 and 20 meters in the Caribbean. So the mesophotic reefs are actually producing, at least now, more material than they are in shallower areas. And so that's a really significant finding, and it adds more power to questioning traditional ideas that reef accretion decreases with depth. However, when we look towards the Holocene a little earlier, we do find that our rates are all less than between 10 and 20 meter depths for coral accretion. And so what that might mean is that you actually do have accretion may have been higher in the past in mesophotic reefs, but at least currently they're not, accretion is not as high as it was in the Holocene, and that probably is attributed to decline in coral cover. And also, I'm just curious to see if you thought about how long these reefs were available to create material based on sea level change. If they were continually producing material, we estimate they'd have at least 6,000 years to be at mesophotic depths. This shows the amount of material that they could produce, and we also provide the value if we use those 2003, the higher coral cover estimates. And we find that they can create a significant amount of material. However, based on the amount of accretion we find, we don't find like in this build up here, we don't think there's enough accretion of mesophotic reefs to account for the differences in structures that we see. We think that it extenuates, it exaggerates original structures that are there, but it's just not enough accretion to create this basic bottom line pattern. And so it's likely that these reefs are still initiating on andesite topography. And we would expect that this is in shallower water, this is more of a lagoon system with patch reefs, and these were the outer reefs. Again, we would need to core, and it's something that I'm very interested to confirm that. But still, the modern mesophotic reefs are still producing significant amount of material, at least 4 to 8 meters of material in 6,000 years. All right, so let's end this. So there was the first question is about accretion. All studied U.S. Virgin Island mesophotic reefs are currently accreting. Again, that's basically a misnomer because the reason we can say that is because they're all in a net positive production status. So basically they're all in a net positive production status, which infers that they're all currently accreting, adding material to the carbonate shelf. There's significant variability in geomorphic production. So some mesophotic reefs in the area produce material based on secondary production from other organisms, whereas other ones rely more on coral. We do have the differences in accretion rates in the variability in geomorphic status definitely contributes to habitat scale of differences in relief, but we don't think that's the primary reason that you have the bank features and the hillocks. And finally, we did find that we likely had higher net production in rates in the past in 2003, and likely due to modern stressors. So the last question, how does mesophotic reef accretion compare to shallow reefs in the past? And what we found was a higher accretion than average shallow water accretion modern in the Caribbean. So that's significant. These deep reefs are creating more material than their shallow water counterparts currently. And this makes us question, again, the traditional theory, does reef accretion overall decrease with depth? However, we did find that our rates currently, our modern rates, are lower than from the Holocene reefs from 10 to 20 meters. And so there might have been a decrease in reef accretion overall in mesophotic reefs since the Holocene, but we can't confirm that currently without having more data. And finally, so on average, we question, are mesophotic reefs at all depths adding less structure to the shelf? And it seems that that's possibly the case. Like I said, based on these results in the Holocene, we would expect similar, if not, we would expect mesophotic reefs from the Holocene time to be higher than they are at these depths, based on the results that we found here. All right. So that's, I hope that made some sense and it was helpful. It's certainly interesting to learn how mesophotic reefs are changing and the carbonate production. So now I'm here in Eilat, and I'm still interested in mesophotic reefs, and there's been great work done, but again, we don't really understand their history. There's been seismic studies to determine, and geomorphic studies using bathymetry to try and understand that there's different terraces in the Gulf of Aqaba. And we want to understand when the initiation of these terraces in mesophotic reefs developed, what they're composed of, if they're associated with past sea levels, and if it's their development from a lot of accretion of modern mesophotic reefs, modern being the past 6 to 10,000 years, or if these terraces have been produced at times of lower sea level and represent fluctuations. And so that's the current work that I'm doing at IUI, and we're hoping to get more samples at these deeper depths and try and, it's very hard to try and sample underneath the modern veneer of the reef. Hopefully we can get some cores, but it's going to be difficult, but it's very exciting, and if anyone has suggestions on that, I would love to hear about them, or if you want to collaborate, I'm open to any of that. And with that, I will say thank you. We had a lot of support and funding for this research, and I just want to make sure everyone's thanks for that, and I will thank you for listening to me talk for 45 minutes, and I will be happy to answer any questions you have.
Maybe the way you measure the bioerosion is a bit simplistic, because the way you make this small disk, it hardly imitates the complexity of one coral in its surroundings. So, you know.
You're absolutely right. It's an approximation of the reef itself. There's a lot of problems. We were using a different material than that was there. Usually, bioeroding organisms aren't presented with this nice this right there. And also the other issue is you have material that's in different stages of, some might be older, some might be younger. It's a problem, and it's funny because Robert Ginsburg was my original mentor, and he wanted to write a paper with me, and I almost agreed with him on why carbonate budgets are bad methods. They are not great. To try and account for every possible scenario and everything, it's impossible. This is our best guess that we can do, and there's a lot of flaws in it. The important thing is that, A, we're using the same method for all different reefs. So at least when we compare between sites, we're at least getting a decent approximation when we compare between the sites. And that was my initial goal. But I did want to expand and look at accretion. So that's where it gets a little more difficult, because then you're looking at a lot of different approximations. It's a lot of published papers have done the same thing. I'm not going to say they're correct. So at least we're comparing our bad methods to other bad methods. And again, as we start learning more and more about these systems, hopefully, and more complexity, we can add and correct these models. But at least this provides a first estimate of potential accretion in mesophotic reefs and direct measurements. And hopefully it starts stimulating more discussion and gain people interested. And obviously, there's just so many more techniques to use. There's CAT scans. I wish we could have done CAT scans, but even then you have problems because you have the issues of and then are the circles right? There are people have debated if you should use cubes or circles. So there's all sorts of issues, and I'm glad you identified that. This is our best approximation.
Yeah, how do you think the results are going to be sensitive to changes in, say, CO2 and ocean acidification, things like that?
So, in mesophotic reefs, there's been really little work on changing with acidification. It's mostly been done in shallow water. So I really can't answer what is going to happen in terms of the production. In terms of bioerosion, you tend to have accelerated bioerosion. Acidification facilitates these processes, the chemical processes. But you would really need to look at it from a holistic approach of both components to compare. So it's hard to speculate. At the moment, I don't think that the big difference is going to be a comparison between shallow and deep water. I don't think it's going to be a huge contributor at the moment for deep reefs. But again, that's just my speculation. We really don't have much data on acidification in mesophotic reefs, so we can't really answer that much. But it is an important question. I also think, as you saw with the results, that the deeper reefs are accreting more than some of the shallow reefs. That might not have been in the past, because in the past we didn't have these anthropogenic influences, right? And so maybe the modern studies that we're looking at production, maybe the production is poor because coral cover is a big part of that. And so if you have pristine reefs, the approximate accretion might actually rival that of mesophotic reefs. So it is an issue to consider. Actually, it's a very good issue to consider in terms of comparison between deep and shallow. But we just don't have enough information.
What about other anthropogenic activity? What are the other potential activities that can affect the results?
It depends on specific mesophotic reef system you're looking at. So storm impact is relatively minor here. We don't see much terrigenous sediment. We did another paper on sediment analysis here, and there's almost, it's all a volcanic island. We didn't find any of that in the sediment. The storms aren't really reaching there. In other places I've worked, you've had a lot of storm damage, even at those depths. So it really depends. Here, I don't think that that's a big influence. You don't have a lot of fishing there because it's a restricted area. You're at least 15 kilometers from shore, so there's not much diving there. So in terms of anthropogenic, the mesophotic reefs in this location are pretty pristine. I mean, these are some of the nicest reefs I've ever dove on. I mean, they're beautiful, and I think they're really removed. But again, here in Israel, you have a lot more sediment potentially causing problems. And again, you have to factor what are the positives and negatives. That sediment might actually help in terms of accretion, adding more carbonate from, it might take the carbonate from shallow areas and contribute it more to terraces of deep water. So you might have more accretion. So it really depends on the system itself. It's hard to answer, but a very good question. Again, we're just at the surface of understanding. And I hope people are interested because there's just so much we could do and learn. There's a lot of modeling that you could do to ask these questions. What if we did this? What if we did that as well?
Any more questions? Thank you very much.
If you have any other questions and you didn't want to ask or any suggestions, feel free to come up and ask me. I'm happy to talk.